right, let's go and get started. So a couple things. Let me get the lights and whatnot adjusted. Okay, so if you haven't already done so, go ahead and start a pile right here. Get all your homework and whatnot turned in. Excuse me. So what I'm going to do is really quickly go through the solution. I think probably the problem that gave everybody the most headache was the composite beam, so I'll talk about that one a little bit in detail. But with problem one, the big thing you just had to ensure is that you were using the appropriate C distances. You were given your moment of inertia. Here's your centroid, so the section modulus for the top of the section is I divided by the 0.617, and I divided by the 2.269 is your section modulus for the bottom. And I think that was really the only, I guess, funky part associated with that. Okay. Let's see, I think this one was pretty straightforward. It was all about just solving for section moduli. The big thing you had to do is just ensure that, you know, you assume a weight, but you have to go back and update that weight because when you select the section, you didn't know what that was. So for instance, when you first start out, if the first thing you pick is a C12 by 30, you have to add an additional 30 pounds per foot because that's how heavy the section is. So when you do that, you find that first section doesn't work and you update it to the next one and you find you're good to go. This one I think was the one that was the funky one. And the long and short of it is this, okay? The first thing you've got to do is you've got to take this wooden plank right here and you have to turn it into steel. And what you end up doing is you end up taking this and squunching it down, making it thinner. In fact, it ends up looking something about like this. And the width of that ends up being 8 inches divided by your modular ratio, which if I remember correctly, that all comes out to be 0.32 inches. So once you get that, you say, all right, here's your datum, and then treat it like it's any moment of inertia problem. You know, you say, okay, here's the shape, you know, here's your area, here's your y, here's your AY, here's your I naught, here's your D, and then here's your I plus AD squared. The same thing we did on that last homework, so it's the same story, okay? And as for the properties for the angle, you just look those up in the back. Now, I will admit, the way that the table is in the back, it's a little unclear what axis you're looking at when you're looking at an angle that has unequal legs. So I imagine that there's going to be a little bit of like, you know, using the wrong value here and there, and I'm going to be pretty gentle on grading that because that unequal leg table I think is a little funky. So, but yeah, so there's that. And I think that was the one that caused the most consternation. But once you get that, the problem is pretty straightforward. It's just sigma equals my over I. Okay. All right. Let's see. Problem 4, I think, was our shear stress formula. And again, the big thing is just using that, which we derived, you know, using this right here, which we derived that in class. So it should be pretty much just a plug and chug problem. So that'll stay there if I don't erase it. Okay. And the last one, I think that was it, wasn't it? Nah, better be. All right. So let me go ahead and pass this out, the solution, so that you all have that. Again, if you haven't turned in your homework, go ahead and put that up there. All right, so 1, 2, you all are spread out pretty thin, so I'll be nice. Oh. All right, I'll give these to my TA, and he'll try to get it done as quick as possible. And what I might do is once I get them graded and get the grades posted and whatnot, I may take the homeworks, and I don't know if you've seen there's a box outside my office. I might just sort of throw them in the box, and if you want them to study for your exam, you can just come pick them up. Does that sound reasonable? Okay. I'm going to be lazy on this row. Y'all are a little closer together. There's that. And there's that. Okay. So let's talk a little bit then about our exam review, because we do have a celebration coming up. So let me see. I never got the sign-in sheet started. Let me go and do that. All right. So let me go ahead and pass this out. There's really not a lot on the exam review set in the way of formulas. This is going to be way different than our last exam, because if I remember our last exam with the exam review slides, I had a whole bunch of formulas. And I don't think I'm going to have as many formulas for this one, because I don't think that's really what this exam's about. This exam's really more about the methodology. Yes, Did I do the wrong, which one? Dash 5. Did I do the wrong one? Whoops. Okay. Well, I'll fix that. What I'll do is this. I'll print out a new one. I'll put some stuff outside my office, and then I'll post it online as well. Sound good? Thank you. I would have missed that. All right. Where was I? Did I get exam reviews to this row? Okay. Yeah. I think I'm at like 4 mistakes this semester, and I'm allowed 7, so I'm still good. No, 7's my limit.
Yeah, I think we've reached that.
No, I'm at 4. You know, it's a conflict of interest since I'm the one keeping the score, right?
I was waiting for a limit fund and never got one.
A what?
A limit fund.
Oh, they'll come. It'll happen. Okay, so let's talk a little bit about the exam. So it's going to be the same format as last exams. You're going to have a series of short answer questions and then 3 workout problems. Okay, you're allowed a calculator and a formula sheet. Remember, you can put whatever you want on that formula sheet and just no worked out examples. I think that'll hurt you more than help you. Also, excuse me, a straight edge is probably going to help with shear and moment diagrams. So I would make sure you have something that can draw a straight edge. What else? Try and be on time. We're going to start at 8 a.m. sharp, and if everybody's here earlier, we'll start a little earlier. I'm not a freak out when it comes to time, but we are going to end, at 9:15. But if everybody's here early, we'll start early. One thing I'll point out, any necessary section properties of simple shapes and rolled steel sections will be provided. Now, I'm not one of those guys that's going to make you memorize all those formulas. That being said, remembering that the moment of inertia of a rectangle is bh cubed over 12 is probably not the worst idea in the world. Some of the more basic ones, it would probably be a good idea to at least have a good handle on. I'm not going to I don't want you to memorize the moment of inertia of a parabolic spandrel or something. There's no point in that. That's what looking up in tables is for. But some of the more basic ones, it's probably a good idea to at least have a good, mindset on. As for what's on the exam, let me get that little thing out of the way. It's bugging me. All right, so geometric properties. Make sure that you can compute the moment of inertia and section properties of basic shapes. And the big thing you need to know how to do is the parallel axis theorem. The sum of I plus AD squared will give you the I for the entire section. As for statics and beam analysis, you need to know how to compute support reactions for concentrated forces, concentrated moments, distributed forces, anything containing a pin, roller, or fixed support. Now last, you need to be able to draw shear and moment diagrams. Now, unfortunately, I don't really have much in the way of formulas for you for that, because there are no formulas. It's sum of forces in the x direction, sum of forces in the y direction, and sum of moments. And if you got that, then that's about it. I mean, there's really just no formulas. As for beam stresses, there's really 2 types, bending stresses and shear stresses. And the big complication with bending stresses is that you can handle both a homogeneous structure and a composite structure. Now, the difference between the 2 is that you transform one of them using the modular ratio. So make sure you know sigma equals my over I. Make sure you know that maximum bending stress is m over s, your section modulus, and that your modular ratio is typically taken as E of the stronger material over E of the weaker material, so it comes out larger than 1. And make sure you can do shear stress. It's tau equals VQ over IB. You can also use the one for the rectangular cross-section that we derived. That's it. That's exam 2. So here's what I'm going to do. I'm going to do the same thing that I've done in previous exam sessions. I'm going to let you all ask whatever you want, and I will do my best to answer those questions. Now, you can ask me what problem number 1 is. You can ask. I'll say no, but this is your time, so ask whatever you want.
What kind of problem where you transform like wood into steel or
Okay, we can do that. Do you want to go through the homework problem? Is that what you want to do, or?
Yeah.
Okay, all right, we can do that. All right, let's do that then. All right, whew. Thank you. Put that right here. While I'm pulling this up, are there any other conceptual questions? I want to make sure I'm using the time as much as I can. Okay. What was the number of the problem? Right. Shut up. Okay. Okay, so a couple things. First off, before we do any math, we know that E for the steel is 30 times 10 to the 6 psi. And we know that E for the wood is 1.2 times 10 to the 6 psi. Sound good? Okay, now, I can use these to calculate the modular ratio, which is going to be 30 times 10 to the 6. Goodness, what's going on there? Looks like my pen's cutting out. 30 times 10 to the 6 psi over 1.2 times 10 to the 6 psi. Now, just from a calculation standpoint, I can just say that's 30 over 1.2 because everything else cancels. So that comes out to be, I think, 25. Am I correct? Okay. All right. Now, I might pull up some Excel here in a second just to automate some of our calculations, just so I can go through it more quickly. Is that okay? All right. Okay. Now, I'm turning the wood into an effective lump of steel. So I want you to think about that. The last example, we turned those steel plates into wooden plates. And we did that by making those those plates larger, right? Because the idea was you need more wood, to get the same effect that you would out of that steel. Well, since we're working oppositely, we're going to take that wooden plank and make it thinner, okay? So the idea is this. If I have, an angle and an angle, and I have some wooden plank, like that, the idea is that I'm going to, the idea is I'm going to transform that into a section of the same material, but I'm going to make it thinner. Do that. Okay. Does that make sense? So I'm going to take this and make it thinner. So if you remember, this was 2 by 8, and this is going to be 2 by 0.32. Now, how am I getting the 0.32? I'm saying 8 inches divided by n is 8 inches divided by 25, which comes out to be 0.32 inches. That make sense? Yes, sir. That's a good question. And the answer is, let me answer it like this. Okay. Why is it that we're changing the width and not the height? Okay. The reason, what's that? You're on the right path, yeah. The reason why is, okay, remember, when I compute a moment of inertia, I've got to pick a datum, right? Make sense? Same here. Now what I'm really interested in doing is taking the area and making it smaller. Now I propose that there's two ways of doing that. I can either make it thinner, you know, or I can do that. Make sense? The problem is this, okay? When I determine my centroid, I need this moment arm to stay the same because I want to get that same effect. And the only way that I can change that area such that this moment arm is the same is to make it thinner. Now that's because I'm measuring my distances this way because I want the moment of inertia about the horizontal axis. Now if I wanted the moment of inertia about the vertical axis, it would be backwards, and then that's what I would do. Does that make sense? So that would be a more elaborate and detailed answer to your question. For this example, no, because we want that moment arm that way to be the same. Make sense? That's a good question. Everybody good? Okay. Now, let me see. All right. Let's see. Which one? Was it Appendix F? Yeah, okay. Okay. Here's the properties of angle sections with unequal legs, and I believe we're after this 5 by 3 by 1/2, right? Okay. Now, what bugs me is this image right here. I don't think it looks appropriate. What I think it should look like is this. I think it should look like this. It should be like that, and it should be like something like that. In other words, you know which side is the long leg and which side is the short leg. I think that's too, they look too much alike. I question the artwork. And honestly, I could see where looking up some values might be a little funky. Okay, so I'll give you that one. But one thing you should know is this. Okay, let's look at this problem like this. Okay. Let me just ask a question off here to the side. If I have a rectangular section being subjected to load, which section is stronger, the one on the left or one on the right? Left. It's going to have a much larger stiffness, right? Make sense? Now, I'm going to draw this in an exaggerated fashion, but you'll see why I'm doing this. So, in that same light, which angle is stronger? The one on the left or the one on the right? One on the left. Okay. The reason why that's important is this. If you look at the problem in the textbook looks like this. You have a plank and you have an angle, but the angles really look like this. You know, this is the 5 inches. And this is the 3 inches. So they're facing long way up and down, right? Make sense? So the angles are being oriented along their strong axis. Everybody okay with that? The reason why that's important is, I know that image is going to come along with me. I'm going to have to erase this because it's going to get confusing. All right. The reason why that's important is because if I'm looking at this set of data right here, right? Because that's the L 5 by 3 by 1/2, right? I need to look up properties associated with, oh, I went over one. I need to look up properties associated with this. Let me erase a little bit. Now, why am I doing that? Because of this right here, axis 1, 1. Okay, that's the strong direction. Make sense? Okay. So, what do I know about this? I know the area is 3.75, right? I know I is 9.43, and I know this D distance. Everybody okay with that? All right, so let me write that data down. So 4 and L 5 by 3 by 1/2. I have area is 3.75. Wait, was it 3.75? And this was 9.73. And D is what? 1.74. Everybody okay with that? Okay. Now let me go back to the slide real quick, or to this real quick. All right. Whew. I made a mess. Is that what I put? Yeah, 9.43. Okay, 9.43. Sound good? Okay. Now, let's look at something real quick. When I determine a centroid, okay, I need to determine those distances with respect to the datum. So my y distances go from the datum. Let me ask you this. How far is it from the datum to the center of that plank? Well, it's 5 inches and then 1, so it's 6, right? Everybody okay with that? Because if I draw this in a little bit more of a detailed fashion, here's that. Bless you. And I'm looking for the distance right there from there. That's my datum. Doesn't matter. You're exactly right. As long as you're consistent. Exactly right. You could have put the datum at the top. You could have put the datum right there. Doesn't matter as long as you're consistent. I like doing it at the bottom just because I know all my distances will be positive. And from there to there is positive. If I put it at the top, the distances will be negative. Oh, yep. You're right. Oh, dang it. And that's in inches. Yep, you're right. Okay. Now this distance here, that distance is 5 inches, and then this distance is 1 inch. So that y is going to be 6. Everybody okay with that? Now, how far is it from the datum to right here? Okay. Now you're going, well, what's right there? That's the centroid of that angle. Okay. Go back to this. Remember, here's the angle right there, and the centroid is right there. It's on the outside. Okay? So how far is it from the datum to that centroid? Well, it's all about this right there. Okay? From the back end of that leg to the centroid is D. Okay? So I propose to you, well, what I propose is, yeah, this distance is 1.74. So to get from here to here, I'd say like that 3.26. I do that right? Yeah, because 26, I'm almost thinking like when I was worked at a convenience store, another 26 cents will give you $2, and 3 will give you $5. So 3.26. I used to work at a convenience store, and I used to be able to do that real, super quick. All right. Everybody good? Okay. So everybody all right with this? Everybody all right with this data? If you're all right with this data, then everything else is rote. Okay? So let me show you. Okay, so okay, so this section has 3 shapes. It has the plank, whatever you want to call it, the board, the plank, whatever. It has the left angle, call it left angle, and the right angle. All right. Sound good? All right, so we'll shade that up a little bit so we know what's up. Okay. All right. So let's start off with the areas. Okay, now what was the area of those angles? What was it? Okay. Now the area of the plank is going to be 2 times 0.32, right? So sound good, right? Okay, now centroidal distances. How far is it from the datum to the centroid of that plank? 6 inches, right? Now how far is it, bless you, how far is it from the datum to the centroid of each of those angles? 3.26. So now we just say equals that times that, that times that, that times that, right? Then we can just sum that up. That's what we get. So far, so good? So that times that is that times that is that, and so on and so forth. There we go. So I can calculate y bar pretty easily. I can just do that by saying sum of AY equals sum of AY divided by sum of A. Okay. It's really dark here with the lights. It's kind of tough to see. Okay, so that's my centroid. Sound good? All right. Now let's do the moments of inertia. What were the moments of inertia of those angles? What was it, like 9 point something? 9.43? Okay. Now for the plank, width times height cubed over 12. There we go. So equals the width times the height, which is 2 and then cube that over 12. That's what we get. Did I do that right? Yep. Okay. D distances, remember you just take your centroid minus each one of those. So you can do that by saying equals the centroid minus that. And since I want to copy and paste, I might want to hit an F4 on that to lock that cell in. And then I can just copy and paste. And you notice it's still locked in that centroid. And then what do? You say equals I naught plus A times D squared. And then sum it up. There's your moment of inertia. Whoop, no. And there's your moment of inertia of the section, which I would hope is what they got in the solution. That's not what they got? Oh, I think I know why, because they turned the steel sections into wood. Yep, that's what they got. Yep. Let me see something real quick. Yep. See, what did they get in the solution? They got what, 588? Yeah. The reason why they did that is because they turned the steel shapes into wood, and the difference is what happens if you take this and multiply it by the modular ratio. What's the modular ratio for this? So they got 587.5 or 588. I think it's easier to do this. Yeah, because what they did is they were turning the section into equivalent lumps of wood. I think it's easier to just turn that one section into steel and deal with it like this. Oh. Well, no, that was right. That was right. Yeah, no, I can appreciate that. Yes, sir. This was, all right, so for right here, you're talking about this one right here. Okay, so it was just BH cubed over 12, which is 0.32 times 2 inches cubed over 12. Yes, sir.
When you change the wood to a steel, there's nothing like a U shape.
Mm-hmm.
But if you change the steel to wood, there's an L shape.
That's why I don't do it. I think it's a little more confusing. What they're doing is just adjusting the appropriate numerical values, like taking the area and just saying, okay, this times 25. I think it's harder to visualize, which is why I don't do that. And this is very common. Here, my rule of thumb is this: when there's more steel than there is wood, and the properties make sense, convert back. When we do section properties for bridges, we usually have 4 components we have to deal with: a top flange, a web, a bottom flange, and the concrete. Instead of turning all those into concrete, I just turn the deck into steel and just keep it simple. Does that make sense? So in the end, it'll work. It's not like either method is incorrect. I just think this is less hassle. That's me. That's just my preference. There's nothing wrong with turning the angles into wood and getting 588, because when you calculate sigma equals my over I, you're going to factor that into it later. You see what I mean? Yes, sir.
So what's your final answer? I thought we were solving for A.
Okay. All right. You're right. This isn't the final answer. Okay. All right. Okay. So here's what I want to do. I want to say, come on. I want to say, after calcs, we have I equals 23.5 inches to the 4th, and we got that Y bar was, what was it? 3.475. And I'm going to say measured from the bottom. Okay. All right, sound good? Everybody okay with that? All right. Now, I want to go back, and this is something we did, with the wooden beam earlier. I want to make sure we understand something. Okay. So, let's see. Maybe I should get my scale right. And I'll draw this as it really is. Oh, come on. I can do better than that. I'll use a different color. So that's our section, right? Okay. Now, the centroid is somewhere about right there, where this distance is 3.475 inches. Make sense? Okay. So let's do a little bit of a review. What's that distance going to be? Five minus that. So what? 1.74? Would be 5.525. Something like that, right? Sound good? Okay, now, just so we're aware, what is this distance going to be? 3.525? All right? So Everybody okay with that? Any questions? Now, let's start off with drawing the strain profile. Now, pop quiz so that everybody's aware. What is so special about that centroid? The centroid is the location where there's zero strain and zero stress, right? There's no stress or no strain at that centroid. So if I look at the bending strain profile, it's going to look something about like this. It's going to go like that, and then like that, like that. It's going to go like that. That's the bending strain, right? But that's not the bending stress formula, because what happens from here to here? You know, what happens at this point right there? Well, right at that point, if I'm looking, you know, above the section, right there the section suddenly jumps from steel to wood, right? Make sense? Now, wood is a material that is significantly weaker. So what's going to happen is that to develop the same strain, we don't need as much stress. So there's going to be a jump in stress right here, and it's going to get smaller. Okay? So here's what the stress profile is going to look like. It's going to look something about like this. All right. Let's see what I can do. You can go about like that. Like that. And then right here, where we suddenly get weaker, the stress is suddenly going to get smaller. Still going to increase up a little bit. And it's going to go like that. Does that sound good? Now, if that sounds a little strange, let's go back to this. Let me find the example. Nope. Yeah, right here. Okay? Remember here when we were looking at this section, when we did our transformation, we turned this into a larger element, right? That got bigger. So the stress suddenly got larger. Here, we did the inverse. We took the wood element, we made it smaller. So the stress is going to suddenly get smaller there. Does that make sense? Okay. All right. So now, one other thing. See how we have sigma equals my over I and sigma equals my over I times n? Everybody see that? Over here, here, this line right there, that's going to be sigma equals my over I. This line is going to be sigma equals my over I divided by n. Does that make sense? Because it gets smaller. Everybody okay with that? Now, let's look at this real quick. Based on these numbers, where is the maximum stress for the wood going to be? And here's the wood. Is the maximum stress for the wood going to be at the bottom or at the top? The top, right? So right here, that's sigma max for the wood. Make sense? Now, based on these numbers, where is sigma max for the steel going to be? Is it going to be at the top or is it going to be at the bottom? What's that? Well, no, think about this. How do you calculate the stress? Sigma equals my over I. Which has the larger y distance, from here to here or from here to here? From the bottom, right? So this right here, this location right there is sigma max for the steel. Everybody okay with that? If you're okay with that, then the rest is going to be very plug and chug. All right? All right, let me show you how this works. We take each section one at a time, check it, get the worst case. So let's start off with the steel. All right? Okay? Now, we're trying to find the moment. Okay? We know y, and that's 3.475 inches, because we got that right here, right above that. You can see that right there. And we got our moment of inertia is, what was that, 23.5? Right? The only thing we need is a limiting stress. And going off the problem, what was the limiting stress for steel? What was sigma allowable for the steel? 12,000 psi, right? No, we don't do that. We're going to keep our numbers as is. Sound good? Okay. Now, here's our expression. Sigma equals my over I, right? What do? I solve for m. And what do we get? It'll be a big number. All right, that's good enough. 81, 151. And what are the units going to be? This is a moment. There we go, inch pounds. To divide or to turn it into foot pounds, we divide by 12. So 67, 62.59 foot pounds. And if we take that and divide it by 1,000, 6.76 foot kips. Make sense? Everybody okay with that? Now, let's go back to our example that we did in class. Remember, we did this. We made a guess that the steel governed. And then we said, all right, let's take that moment and then check the wood, right? And we found that that wasn't the case, so it was really the wood that governed. What I'm going to do is something very similar. This would be the moment that is required to cause failure in the steel. Make sense? Now let's look at the moment required to cause failure in the wood. So we don't know the moment. Now our y distance. How far is it from the centroid to the worst case location for the wood? 3.525. Remember that right here? From there to there is 3.525. Everybody okay with that? Now, we have a modular ratio and sigma allowable. What was sigma allowable for the wood? What is it? 1,100? Sound good? So now we do the same thing. Sigma equals my over I, but since we transformed this into steel, we have to divide. Make sense? All right, just solve for M. Oh, we got 23.5 to the fourth, 25 over 3.525 inches. And what do we get? Let's see. Okay, so what we're finding is that, hold on, let me see something. Oh, they got a different answer. What's that? Did we do a calculation wrong? Oh, they had, yeah, no, yeah, okay, no, we got the right answer. They converted this to inch kips, and they said 81.1. Okay, all right, okay, that makes me feel good. All right, so, all right, what I want to do right now is look at this. I want to look at this number, and I want to look at this number. Which is the worst case scenario? This one, right? In other words, if I start bending this section, I'm going to fail the steel before I fail the wood. Make sense? So I propose that the maximum capacity of this section is 81,151 inch-pounds. And you can convert that to your heart's content. You can say 81.151 inch kips. You can say 6.76 foot kips. Whatever. Whatever unit you think makes sense. Is that okay? Now, does that make sense? That's a challenging problem, but that was kind of supposed to be. So it was trying to test your abilities on this bending stress formula as much as possible. So let's sort of take a breath. Does anybody have any questions on this? Because I really want to make sure you understand this. Mm-hmm. Yes, exactly right. That's exactly right. And the reason why is this. Ultimately, we don't really give a damn about where the datum is. In other words, we don't care about these distances. We care about these. Now, here's a proposition to you. I propose if I change the datum, let's say instead of putting it at the bottom, let's put it at the top. I propose to you that these are going to change. And I propose to you this is going to change because it's going to be measured from the datum. But these won't. These will still be the same because what are these values? These are the distances from each individual centroid to the centroid of the whole thing. This is where we wash the error from where the datum is out. That's where that goes away. You know, you could think of it like this. We start off making a guess that the centroid is at the bottom. That is certainly not the case. Actually, it's 3.475 from the bottom. But when we subtract that out, we're saying, okay, those are the distances from that centroid. So where the datum is doesn't matter. You will still get the same answer because you're washing that out with those. That's a good question.
What's the formula for D?
For what?
Or what did we say?
Oh, for the D distances?
Yeah.
So if to get this number, we'll call that D1, since this is shape 1, that's shape 2, that's shape 3. We take the Y1 minus the Y bar. So this minus that. Right? It doesn't matter because what are you going to do with this? Exactly. It doesn't matter. See? So, and then See, it doesn't matter. That's a good point to make. It doesn't matter whether you go forwards or backwards. I want to explore this and make sure this makes sense to everybody, okay? But I do want to make sure I'm answering all your questions. I mean, I know that this was a long example, but I also believe that this example has a lot of stuff in it that covers a lot of things that are on this exam. Moments of inertia, the bending stress formula, there's a lot of stuff there. But there's still other things. There's shear and moment diagrams, there's shear stresses, so I want to make sure I'm using my time appropriately. Y'all have any questions? I mean, this is the time. You mean this?
Not on this problem, just what is it exactly used for?
This is the parallel axis theorem right here. Here, I'm going to erase some stuff because this is going to get cluttered. This is the parallel axis theorem right there because I say it's I naught plus AD squared. I mean, look at what I have in the cell. Is this right here for little shape. Yes. The A is the area of that shape, and then D is where we washed out that centroid distance. And this is the moment of inertia, the whole frickin' thing. Yeah. Now keep in mind, this is the moment of inertia assuming that the whole thing's made of steel. If we assume that the whole thing's made of wood, we're going to get this times 25. But when we calculate our steel stresses, instead of using sigma equals my over I, we're going to have to multiply that 25 out again. Does that make sense? So whether or not you consider it as one big steel cross-section, that's another point I want to make to kind of further answer a question raised by Leo. If you turn it into a wood cross-section and you get a moment of inertia that's like 580 something, will you still get the same final answer? You know, moment is 81.1 inch kips, and the answer is yes. Because regardless of whether you turn it into a big steel shape or a big wood shape, you're still going to find the worst case moment is for the steel, and it comes out to be 81.1 inch kips. It's just whether or not you multiply by 25 or divide by 25. That's it. No, I can appreciate that. That's a little, it's a little funky. I can appreciate that. Yes, from your datum, wherever that datum is. So if you put the datum somewhere else, you will get a different y bar, but it'll be in the same physical location. So like if you put the datum, let's say, right at the top of the angles, you might get a y bar that's like negative 1.525. So you start at the datum, go down, that's the same spot. Yes, sir?
How can you tell when you're doing a bending moment diagram and a shear diagram if it's going to be a positive or negative graph?
The simplest answer is look at the loads and imagine if the beam deforms under those loads. Is it going to look like a smiley face or is it going to look like a frowny face? If the beam looks like it smiles like this, then your bending moment diagram should be above the line. In other words, like, let me minimize this. In other words, like this, okay? If you have a beam that looks like this, okay, and I decide to put a load like that on the beam is going to respond by getting kind of sad, right? It frowns. When you look at the moment diagram, it will look like this. because all those values are negative, right? Because think of it like this. This is your x-axis, and that is your y-axis or your moments, right? And they're all negative. Does that make sense? That's the easiest way to just, you want a quick, is this what it looks like? There you go. Well, think about it like this, okay? So let's say you put 10 pounds like that, right? If it's smack dab in the middle, you got to hold that table down 5 pounds here. You got to hold that down 5 pounds here, right? Okay? So your shear diagram is going to look like this. You're going to go down 5, over, up 10, 5, down. All right? Then whatever area this is a negative area, that's positive, so you go down and then back up. Yeah, remember, to draw the moment diagram, the values come from the area under the shear diagram. And if you want to use the calculus, go right ahead. I like area of rectangles myself, but I mean, I reached my limit with that stuff a long time ago. There it is. All right. Well, we still got time, so I want to ensure that I'm answering all your questions as much as I can. I want to see y'all do well in the exam. It's so much easier to just, give to not count anything wrong. But then again, if I wanted to be truly authentic, it's easier to give everybody zeros than to give everybody hundreds because it's less writing. You just do 0. More office visits. That's a good point.
Just add the one extra line to avoid office visits,
minus 0. That's a good point. Somebody said, well, why don't you just do a check mark? Just do that. There's no numerical quantities associated with the check mark. I might as well just put the sunshine stickers on everybody's. Like you get a stormy cloud, I'm sorry. Somebody said something. There will be some, yes. There'll be a series of short answers, just like on the last exam. There'll be like problem 1 that'll have a 4 or 5 or whatever, and then 3 workout problems. What's that? Well, the funny thing is, on average, that ends up happening. Like, on average, when I give my exams, the students do worse on the conceptual problems than they do on actually grunting it out. Like, how about this? In a rectangular cross-section, where's the maximum shear stress? Maximum shear stress. Okay, VQ. That was a political answer to that one. Hold on. I'll show you a picture, and then you'll go, oh, that's what he's talking about. No. Okay, that's a good guess. The bending stress is highest on the top and bottom. Let me pull up a picture. At 0. What do you mean at 0? At the centroid. Remember this? Remember that your bending stresses are largest on the top and bottom, but your shear stresses are largest at the middle. Remember that? But that's a tougher example of one of my conceptual questions. That's a more difficult one. Because that one takes some thought. That one does take some thought. what I would do is go through the notes and just try and highlight some of the big concepts and make sure you're understanding the big ideas. You know, like how do you draw a moment diagram? You integrate the shear diagram. So, you know, if you understand that relationship, if I ask you a question about it, you'll be able to work your way through it. You see what I mean? Just, you know, make sure you have a grasp on just the ideas. I'm not going to do some derivation or anything like that. I'm more interested that you understand patterns and just have a gut understanding. And I don't think I'm particularly harsh on the grading on it. I mean, I'm not going to give you full credit if it's wrong, but one thing I will say, if you don't put anything down, I don't have anything to grade. You know what I mean? So put something down, you know. Now don't put like F equals MA or something. I'm like, well, that's that, or don't put Wombo, whatever the heck Wombo is. I don't think I'm going to give you credit for that. But in all honesty, give it the old college try. Yeah, don't give it the old college try, you know. You might surprise yourself, you know. You might, I have no idea. I'm just going to put this, and I go, that's actually the right answer, you know. So.
You'll get half credit. It's like how did you derive it? Okay, try integrating it.
Yeah.
Always integrate. When in doubt, integrate.
Yep.
Even this paper, if you don't know it, integrate.
Or in dynamics, did you try setting the force is equal to 0? Is it not moving?
Did anyone get that problem?
Nope. I don't even know the problem you're talking about. I already know the answer now.
Okay, so we had this problem in the Learning Center, and we all got to the same points, and we said, well, how do we relate these two?
You know.
I have no idea.
Right.
Dr. Bennett comes in, he looks at it, he says, I have no idea how to do this problem.
But he sat down and he goes,
He says, I seriously have no idea. Just go home. And he sent out an email that told us to relate the tangential, which doesn't tell us anything about the normal. Well, we're still stuck.
4.23 times pi squared. Sounds good to me. Don't ask me. My stuff sits still. At least I hope it does. Well, if I'm the designer of a structure and it fails, I'm going to be in, you know, Costa Rica or you know, Guam. Guam's an American territory. I'm going to be fleeing the country, so I'm going to be, you know, somewhere that's not in America. Probably somewhere that doesn't have an extradition treaty. So, you know. Okay, no politics, no politics. No politics, no. Bolts, that's what we're talking about here, bolts and welds. All right.
joking today, please. Yeah. Where's the fist bump?
I'm going to use that in steel design in some, I'll probably edit it a little bit, and then once you're gone, I'll take complete credit for it. So, all right. We still got a few more minutes. I want to ensure that I'm using, you know, the time as wisely as possible. Do you all have any other questions about anything?
You don't give us the answer to number 1. What about number 2?
Fresh out.
Exam is
Tuesday, 8 o'clock. If everybody's here earlier, we will start earlier. But at very least, I'm hit and go at 8 o'clock. Do you all feel better about the exam after today?
There's only one more question.
Yeah, that's it.
Some forces equal 0.
All right, if that's it, don't forget, if you haven't put your homework up here, I need it. We'll see you on Tuesday.